We often picture software development as a straightforward assembly line. A brilliant architect draws up the design, and a programmer simply types it out, translating those abstract concepts into machine instructions. But treating coding as a simple translation task is a trap. When developers prioritize syntax over structure, the system becomes brittle. It loses the ability to withstand the pressure of future feature requests and bug fixes. Code represents the final concretion of the design. As abstract architectural ideas solidify into physical syntax, poor structural choices are baked into the product. If the logic is disorganized, the system actively resists modification. Coding is an active engineering construction phase. It requires adherence to physical constraints, well-defined data structures, and proactive validation before a single algorithm is executed. Failing to treat code generation as a rigorous construction activity is a primary driver for software projects collapsing under technical debt. Building resilient software requires mastering 4 distinct engineering vectors, both before and during implementation. Preparation involves validating the environment and understanding the hard constraints of the problem before any syntax is written. Second are the programming conventions. These define the explicit rules for how the code is laid out and formatted to ensure clarity. Third is the internal design for maintainability. The logic must be organized so future engineers can safely adopt the code without breaking functions. Fourth is documentation. We treat this as a testable item, as critical to the system's health as the binary. Overlooking these vectors increases the probability of systemic decay and raises the cost of every future modification. The construction timeline begins in the preparation phase, long before the first line of source code is generated. Language selection is driven by preference, but must be dictated by hard constraints, like embedded devices versus web applications. Data structures, interface protocols, and architectural conformance guide the team toward the optimal choice. With the language selected, the focus shifts to establishing the testing framework before writing the logic. Unit tests defined up front act as physical guardrails. They force the developer to define exactly what the component must achieve before construction begins. This rigorous preparation allows the team to resolve foundational errors before logic is implemented. Once active programming begins, the process is governed by a core engineering objective: keep it simple. Simplicity is achieved by constraining algorithms using structured programming principles. This replaces unpredictable jumping logic with clear linear paths. Deeply nested logic is extracted into distinct, independent subfunctions. This ensures the component remains mathematically testable. Local coding standards, precise variable naming, and clean visual layouts enable the creation of self-documenting code that is immediately accessible to others. At the component level, we aim for high cohesion. A cohesive module does exactly one thing, focusing on a single targeted function or subfunction. We also strive for low coupling. This minimizes the dependencies and connections between components, reducing the likelihood of error propagation across the system. Adherence to structural simplicity, high cohesion, and low coupling provides a mathematical defense against unmaintainable spaghetti code. Maintainability is a primary measure of software quality. Over time, it accounts for the vast majority of a product's lifecycle effort. We track this using mean time to change, or MTTC, which indicates how effectively an organization handles updates. MTTC measures 3 phases: time to analyze a request, time to implement the change, and time to distribute the fix to users. High MTTC values often indicate the ripple effect, where a single undocumented change triggers cascading failures in unrelated parts of the system. To prevent this, every modification requires immediate validation through code walkthroughs and the execution of the original unit tests. This validation is paired with refactoring, the process of improving the internal structure of the code without changing its external behavior. A low mean time to change is the direct result of continuous validation and disciplined refactoring. A complete software configuration is built on 3 pillars: the programs, the data, and the documentation. Documentation is not a passive byproduct. It is a critical feature of the system that must be verified through rigorous testing. Formal technical reviews are used to ensure editorial clarity and structural alignment between the written word and the underlying code. We then conduct a live test. This involves using the documentation in real time alongside the executable program to verify its accuracy. The test confirms that terminology matches the interface, system responses mirror the text, and interaction sequences work exactly as described. If the documentation fails a live execution test, the software configuration is defective, regardless of how efficiently the code compiles. The construction phase operates as a proactive defense mechanism designed to prevent systemic decay. Precise language selection and environmental preparation prevent foundational architectural mismatches from occurring. Applying clean programming principles and executing continuous refactoring will actively stop the injection of structural defects deep into the source code. And live-tested documentation prevents operational failures by keeping the user and the system in alignment. Integrating these practices into a unified discipline is the primary method for minimizing long-term technical debt. Professional software engineering requires us to shift our focus from the developer of today to the maintainer of tomorrow. The source code written now is the physical infrastructure that someone else must inhabit, navigate, and modify years down the line. A hacker focuses on typing instructions that get a machine to execute a task. An engineer builds sustainable, readable systems designed to survive their departure. Writing clean, documented, and structurally resilient code ensures the system remains operable long after its initial release. In software engineering, the construction phase is where the survival of a product is decided.